それでは実験となりますのでセミナーを開始いたします。本日、社長を務めますのは九州大学アジアオセアニア研究教育機構横田准教授です。横田先生、よろしくお願いいたします。
はい、ハーシャ先生、ありがとうございます。皆様、こんにちは。本日は、講演者のパンカジ先生がですね、英語でのご発表ですので、英語でお願いできればと思います。先ほどのハーシャ先生からの事前アナウンスにもありましたが、今日は英語から日本語の同時通訳がありますので、Zoom 画面下にある通訳機能をクリックしていただき、日本語を選択お願いできればと思います。また、日本語の講演スライドもチャット内にある URL ページからダウンロード可能ですので、ご活用いただければと思います。それではよろしくお願いいたします。Hello everyone, welcome to Brown Bag Seminar number 176. My name is Fumihiko Yokota, a chair for today's seminar. Today we are very pleased to welcome our guest speaker, Pankaj Sensei, who is an associate professor at the Kyushu University Center for Plasma Nanointerface Engineering. Today's his presentation title is a Low Temperature Plasma Application to Achieve Sustainable Development Goals. Pankaj Sensei will be talking specifically for application of plasma into agriculture sector, such as fertilizers. So now I would like to introduce Pankaj Sensei. Please take a look at the screen, the slide. Pankaj Sensei introduction slide. Yes. As you can see from the slide, Pankaj Sensei amazingly has a 2 doctoral degree. By the way, Pankaj Sensei is originally from India, and he obtained a Doctor of Philosophy in Chemistry, University of Delhi, India, 2013. And then another doctoral degree, Doctor of Science in Plasma Engineering from Graduate School Information Electrical Engineering, Kyushu University last year. Yeah, congratulations, Pankaj Sensei. That's amazing. Good doctor, yeah. And also Pankaj Sensei's work experience amazing that not only working India, Japan, but also his research experience in Belgium and Korea. And he is recognized among the top 2% of scientists worldwide in ranking published by Stanford University. So we are very pleased to welcome Pankaj Sensei for today's BBS. Please join me welcoming Dr. Pankaj Sensei today's seminar with a big sound of applause. Yeah, thank you very much. Sensei. The stage is yours.
Thank you very much for the introduction, Sensei. And I am Dr. Pankaj Attri from Center of Plasma Nanointerface Engineering. And the presentation topic is low temperature plasma application to achieve the sustainable development goals. As we know, there is a plasma, can be blood plasma also. To differentiate, this is the physics plasma, which is known as low temperature plasma. So this lightning in nature is also a plasma, and it's natural plasma which occur in the day to day. And the plasma has a strong connection with Japanese culture also. As we know, the lightning has a strong connection with agriculture. So this is the picture taken from this website. So yeah, and this is somewhat the lightning. I'm not expert on it, but I think this shows the close collaboration, close relationship of the Japanese culture with agriculture and the lightning. So they knows about the plasma many years back, like how the plasma is useful for the agriculture. So I will just say some basic thing that what is plasma? So the plasma is the fourth state of matter. We have a solid. If we increase the temperature, we reach liquid. If further increase, we gas, and later is plasma. The plasma is a state where is the ionization occurs. So plasma can be many types, but here I have explained the low temperature plasma. The low temperature plasma is also known as non-equilibrium plasma, which means that the gas temperature is equal to the room temperature. and the electron temperature is more than gas temperature. So the temperature of the plasma is not very high, but the electron temperature is quite strong. And this can help in generation highly reactive species. So the low temperature plasma can generate very reactive species. It can be reactive oxygen species, can be reactive nitrogen species. And second is that it has a synergic effect. So it has the electron temperature effect as well as the reactive species effect. And the major applications, which is industrialized already, is in semiconductor manufacturing. Use the plasma for the thin film processing. And here I talk about some bio applications of the plasma. So as we told, the plasma is, there is a two types. One is the thermoplasma, which is lightning, and the cold plasma. You can say it's so cold that the gas temperature is equal to the room temperature. So you can put a finger behind the plasma. And so they have some characteristics like the thermoplasma required very large volume. So you can have the thermoplasma in sun also, or the lightning. So it need very large volume. Where the cold plasma volume is very low. The reaction conversion is very high, as you know that temperature is very high. So it has electron as well as gas temperature, where it's a little bit low than that of thermoplasma. In thermoplasma, the temperature is more than 10,000 Kelvin, but in cold plasma, it's around 5,000 to 10,000 or less than that. And the last and most important thing is that handling. So the handling thermoplasma is very difficult, where the cold plasma we can handle very easily in our laboratory level. So this is some examples of the plasmas. So as we said, this is the gas temperature and this is electron density. So here we come the low non-thermal plasma, which is around 5,000, which have the glow arc or Glaudic arc plasmas, where the high temperature plasma, when it goes to microwave to arc. So you know the welding is very famous arc plasma, that is the high temperature plasma. And the low temperature, but we mainly focus on low temperature plasma because we want to treat the biomolecules or the sensitive equipments. So where the density is maximum around 10 by 12 centimeter cube and temperature is around 5,000 Kelvin. So there are the many applications of the plasma, as we see from the energy, aerospace, environmental, healthcare, and textiles. And in this presentation, I will focus on environment and agriculture about the plasma applications. So to little bit more, if we try to understand how plasma works. So there is, you can make plasma from different ways, but it can be mainly divided into three measures. One is the streamer, where we have the electrode with the DC or pulse, and there's the target molecules. In jet, it is somewhat similar, but we have the dielectric discharge there. So and it can charges only mainly on the top of the needle, and later to the target we have reactive species. And last is enfilm plasma, where the discharge come between two electrodes. So there is no direct, but it's a remotely reach the electrode. So in these cases, many times the electrons have no much impact, but the direct reactive species reaches the target surface easily. So this is the mode of action of plasma in for the biological point of view. So we have a plasma region where we have electron or positron or negative ions. When that is called the active region, when it react with the surface means the any gas molecules. If it is an air, it can be any feeding gas like argon or helium, anything. Then it can generate reactive species called radicals. And then these radicals can goes to the biological molecule with the water surface. If I want to explain, it is somewhat like this. So this is the case in the plasma where we have some gas. So it can form argon, excited argon. When it reacts with the water molecules, we can generate hydroxyl radical and hydrogen peroxide. If we have the nitrogen gas here, so we can have hydroxyl hydrogen peroxide, but additionally we can have ammonia. In a case of oxygen, in the gas phase, we have atomic oxygen, singlet oxygen, ozone. And when it comes to the water, we can again have ozone, hydrogen peroxide, or superoxide even. In the air, the complication become more because the reaction species are more. So we can have nitrate, nitrite, as well as hydrogen peroxide or hydroxyl radicals or nitric oxide. So we can generate different radical species in control the different radical species with the feeding gases or the environment in this region. And then when it touches to the surface, it leads to the more stable molecule. So as we know, these reactive species are radicals are very short-lived, but they are long-lived, like nitrite, ammonia, they are more long-lived. And they touches the biological surface and leads to the different things like protein degradation or oxidation, lipid peroxidation, membrane, DNA damage, or the breaking of cell walls. So there are many things that can be occur in the biological system when these reactive species touches the biological molecule. But for the sake of here, I am just mainly about the plasma agriculture. The question is this: why we need the plasma agriculture? So we know that the land is constant. We can't increase the agriculture land, although it is decreasing due to industrialization, but the population is increasing. So we need to feed more people in the less land as compared in the past. We have more land and less people. So to that, there is some innovations are ongoing. One of the innovation we feel that plasma agriculture. As we know, the plasma nitrogen is very important for the agriculture. So when the plasma had nitrogen, it can go excitation, ionization, dissociation, or polymerization, and later it can transport to different forms. We called it the functional nitrogens. So these functional nitrogens can have different functions like high functional films, quantum devices, plant functions, and pandemic preventions like use in COVID-19, but I'm not describing it here. So we mainly focus on the plant's new functions, and that leads to the rise of the plasma agriculture. And the plasma agriculture is also cited by different newses like Advanced Science News. We said that the rapid emergence of plasma agriculture, and Science News that told that the cold plasma could transform sustainable farms of the future. So there is a huge scope of plasma agriculture, although it is very quite new, last less than 10 years only the research is ongoing here. So the plasma agriculture can be have both the pre-harvest and post-harvest. And in the pre-harvest, the seed to the vegetative to the plants. In the post-harvest, we have the processing of the fruits to have preservation, etc. So, but in this presentation, I will mainly focus on the pre-harvest applications of the plasma. So the seeds treated by the plasma for very short time, and then we can see some results. Like this is the results of the plumeric tree. After 2.5 years from control to the plasma, you can see the difference in the germination length of the plant. Then we have the rice after 23 days and 49 days. You can see the difference between the control and the plasma. Then this is the yield of the abatos seeds, and you can see there is a 56% increase in the yield. Then we have sorghum plants. You can see here the increase in the germination after the plasma treatment. And these are other plant species which are studied in different studies where we have the growth enhance index from 200 to 100% increase. So that shows that how the small amount of the plasma treatment with just 0.14% of the whole plasma radiation without addition of fertilizer or irrigation. So we can get the increase in the yield. So these are the plasma irradiation effect on the seeds. And in this presentation, I will talk a little bit about both things, the plasma treatment on seeds as well as the plasma fertilizer. So the first one, we can have the induction of plasma responses to the specific to plasma radiation. So the seeds have different responses of the plasma radiation. It can induce DNA modification, and the plasma action can depend from the seed color. So seed coat color can affect. Next, we have the nitrogen fixation on the seed. So we can treat the plasma in air, but we can found the nitrite ion fixed in the seed, so that can help in biological processes. Later, we have the nitrogen fixation of soil, or we can say the formation of the fertilizer, plasma fertilizer. And we can see the increase in the germination of the with the help of the nitrogen fixation to the soil. And lastly, a little bit I talk about the CO2, like we know that the CO2 is very harmful, but we can convert CO2 as a plant nutrient that can help in germination. So the first idea here is about the seed treatment. So we have the cultivation, and the plasma contains ions, ions or photons. So when we treat the seed, the plasma radiation involved in hypomethylation to improve germination. So here is the example. So these seeds are the heat stretched seeds, and in the heat stretched seeds, we have the DNA methylation that leads to the delayed germination. So germination is delayed in these heat stretched seeds. But when we treated with the plasma, we found there is alternation, and there is a high improve in germination by hypomethylation. So the plasma can help the heat stretched seed to overcome its germination problem. Next, we have the sensitivity of the plasma depend on the seed coat. So in the previous slide, you can see the all the germination index is not same for all seeds. So it depends upon seed to seed or seed coat to seed coat. Some are the less seed coat. So we can change the plasma doses or the plasma conditions depends upon the seed, which target seed which we have. And we mainly focus on germination and the growth in our studies. So here is the example, another how a short mechanism, how the nitrogen fixation we can have in a seed. So we taken the lattice seed stored at -30°C. So this is the seed model. And then we treated with the plasma that contain RONs, and then we have omics and the phenotypes. So I'm not going in detail over here. But when we treat the seed with the plasma, we can see this reaction. So there are so many radicals, but the most stable we can have the nitrate ion. So we feel that can the nitrate ion from the air can penetrate into the seed to have the responses. To done that, we done the LCMS of the seed, and we found that after the plasma treatment, there is an increase in the nitrate ion. So this nitrate ion came from the air, or it can generated by the different biological reactions on the seed surface. But we found that the plasma radiation can increase the nitrate ion inside the seeds. So that shows that the radicals generated in the above the seed or in air can penetrate inside the seeds and have some effect. Then the major part of this presentation is the fertilizer production. So as we know that we need the sustainable farming, and the sustainable farming is the fertilizer that is required. So we know that nitrate and ammonia is very important for the plants, and the urea is the most famous fertilizer used in Asian countries. It's worldwide, but in Asia mainly the urea is utilized. And the urea can convert lastly to nitrate ion by the nitrification, but it can also lead to the formation of CO2. So the urea, during the formation of urea, also CO2 is generated, and when the urea is disposed in the water or in the soil, again CO2 is formed. So there can be some substitute of the urea that can be used in the plants for increasing the production. And as we know that it's not directly taken by the plants, so urea is not taken, it convert to ammonia and then nitrate. So nitrate is taken by the plants very fast and then ammonia. So this study showed that the nitrate facilitate ammonia uptake. So nitrate is very important. So why not we just focus on nitrate rather than ammonia or other things? So to understand this, we see that infrastructure. So why we need fertilizer? So as we told, the population increase, but land is constant. So continuous, the productivity is required, and that leads the depletion of nitrogen from the soil. So from the nature, the nitrogen fixation is always there, but due to the continuous use of the crops, the nitrogen depletion has increased. And to solve this problem, there is a global fertilizer consumption is also increased. But to form this, we have around 35 million ton of CO2 is emitted just from the ammonia case. So the different fertilizer, when we goes, the more and more the carbon CO2 is generated, and it is approximate 500 million ton of CO2 will generate worldwide for the fertilizer production only. And it is not included the transportation. So during the transportation of this fertilizer, again, some carbon monoxide is generated in the system. So how this forms. So generally there is two major processes. One is for the ammonia is this Haber-Bosch process, and the Haber-Bosch process requires very high temperature, and there is a emission of CO2 is very prominent here, and which is the main source of ammonia. And next is Ostwald process, which generate nitric acid or nitrate ion synthesis. So for that, we take an ammonia and air, and then we generate the nitric acids. But these have some major disadvantages. One is that methane and H2 is the main ingredient. So methane or nitrogen is the main ingredient here. Next is the fossil fuel. So we need very high temperature and high pressure in the Haber-Bosch process. So to increase the temperature, the fossil fuel is required. Then the greenhouse gas emission and centralized facility is required. So the main thing is that ammonia formation cannot be done at the small industry scale. It needs very high industry scale and very high energy. And as you know that during this Ukraine-Russia war, the fertilizer rate has increased in worldwide market because the Ukraine was one of the major producer of ammonia due to the gas reserves. So the natural gas used for formation of ammonia. So due to this war, already the rate of fertilizer is increased. So we thought that okay, then we just move to the organic farming. And if we just move to organic farming, there are some problems. Like we can see this is the market survey done in Japan by Mitsubishi company and revised by our laboratory. So there is the 93% of chemical fertilizer is required market share, and the organic fertilizer market share is only 7%, which is about the 5.6 billion. So still the market is quite big, 5.6 billion euros for the organic farming. But the problem is there that we can't utilize it, and I will explain a little bit more in the details. So in general, this is the nitrogen cycle. We know that the nitrogen came in air, then during the plasma, it fixes nitric oxides, NOx we can say, and the bacteria fixes in the soil, eaten by plant, then animal poo, which is used as a fertilizer, is general criteria. We can say that how the organic fertilizer uses the animal manure for the fields. And there is another source is the plant extract also used, but in the plant extract, generally the nitrogen content is very, very low. So mainly the farmers, organic farmers depend upon the animal poo or animal manure. But due to the hybridization of the animals, this is also a problem that it can lead to genetic problems. So we need to add another alternative about this. So this is the standard process where we have the NOx and ammonia. So animal slurry, this is rough estimation data in the R algaes, and I have just modified a little bit it. So we have the flesh slurries. Urea can be 40 kilo nitrogen, and organic can around 50 kilo nitrogen. But 10 kilo nitrogen is just goes in a gas in the form of ammonia after just in 24 hours. So it reached 90 to 80. Later, after 90 days, it reached up to 60 only, and rest is converted to ammonium product or released in the air as a form of ammonia. And when it goes to the field, it only reach 40, and 20 again goes to in a gas phase. So we started with the 40, but after 90 days, when it goes in the field, it only left 40. Whereas in organic farming, if we say we have a flesh slurry ammonia nitrogen only, like 50 kilo, then after 24 hours, 24, 90 days, 10, and when it goes to the field, it only left 5. So it started with the 50 and left with the 5. So that's one of the major problem with organic farmers, that the nitrogen content decreased very fastly. So to solve this problem, we just thought that to use plasma fertilizer. So the rest of the things are same, but before that, we added our plasma reactor to treat this, and then we spread this plasma manure. Can be animal manure, this can be plant manure, any other, to the field. We have the extra nitrogen that can be fixed by a plasma reactor to the field, and this can be decentralized. So every farmers can have the small reactor with them. So this is the basic of this study, that we try to fix nitrogen fixation in the plant soil. So this is the low temperature, low pressure plasma. So we insert the nitrogen gas and treated the plant soil, and we found that ammonium nitrate is production is there. So you can see this is the soil treated with the plasma, and this is the control one, and we can have higher yield there. Then we check the shoot or mean weight, and we compare with the commercial ammonium fertilizer. So we found that the small amount commercial fertilizer has a good growth, but higher amount can decrease the growth. So the excess fertilizer is a major problem, as we know, in the soil. So, but in the plasma treatment also, at 3 minutes, it have the better result than the 5 minutes or the 1 minute. So in the 5 minutes, again, it decreases that. It again show that it increase the more ammonia in the soil that can not very useful in our treatment conditions, but we can generate ammonium nitrate with our reactor. So to understand this mechanism, we done the 1D simulation. So this is A and B. This is our plasma coil, where we can have electron reaction in electron impact reactions, and then we have the diffusion. So we calculate that the NOx density can be 2.6 and the NH density can be 2.14. But in the real case, when we go in the soil and we found that the nitrite and ammonia both are increased in plasma treated soil, but the nitrate is not much increase. It's only very less, but the nitrate and ammonia has increased. And then we calculate the energy consumption. So if we take the only discharge power, the energy consumption is around 12 megajoule per mole. But we taken the low pressure plasma, and that contains the vacuum, so it increases quite high. And the second problem is this: in the low pressure plasma, we cannot treat the large scale. To solve this problem, we can have this summary that we can create the plasma, then we have NOx and NH in the soil and increase germination. So our standard protocol is set it, but we need to increase the yield, or we can increase the production. So this is the final. We can have this radical generated in a gas phase, then in a liquid, it forms different radicals. So I'm not talking about the plasma that application, but one of the application is plasma medicines, where nitrite and hydrogen peroxide play a very important role. Then plasma agriculture, we have ammonia and nitrate, but there is another molecule which is dissolved in water, is CO2, and also present in the atmosphere. So the question is that, can CO generated by the plasma can help in agriculture or not? To have this, I've done some literature survey and found that, yeah, CO has some role, but not much studied also. So we taken this CO2 and N2 plasma, treated the water, and that water we treated the radish seeds and checked the germination. And we found that there is an increase in germination and radical spaces, and this is the simulation results. I just finished because it's already late, but we can see that the CO can have an effect. So lastly, I conclude that the seed germination can accelerate the plasma processes, and it has the positive effects. Thank you very much for attention, and sorry I taken a little bit more time.
Pankaj Sensei, thank you very much for lots of information, very informative presentation. We learned a lot, but I wish we could have more time to listen to your presentation more and observe lots of very valuable information, how the cold plasma can be useful for agricultural field, especially for efficient growth of crops and fertilizer. Yeah. So now we would like to have a question and answer session for maybe 8 minutes. Yeah. So for audience, please feel free to drop any comments or questions in the chat box. Any questions is fine. We will be very appreciated. So before we wait for the questions, I have lots of questions. So I think many people are very amazed at this new technology and wondering how much the price for this plasma development machine and safetyness for this? If you can explain a little bit about
Ah,
this. Yeah.
okay, thank you.
Mm,
Thank you for question,
mm, mm,
Sensei.
mm,
Yeah, so the
mm,
cost is we are still in the development stage. So our Privli one is already ready. That is around 50 million yen.
mm.
It's
5000
there.
万。はいはいはい。
Yeah.
うんうん
So
うん。
it's around 5 million yen that reactor, but there is a plasma that we can change. So whole machine we don't need to change. Only the plasma panel we need to replace. Rest of
うん
so one-time cost like the Wilzo company of Japan is now making, and if we increase the production, we can reduce the cost a lot.
う
And the
ん
stability is quite good
う
because
ん
we have only the plasma panel that is easily can run up to 1 year without any problem. And if there is some fault, we can replace it very easily. So it's
う
not
ん
much complicated. Second is thing we mainly focus on decentralization of
う
fertilizer.
ん
So we that small farmers can buy their machine and it can operate on the sunlight easily.
うん
So there
う
is
ん
no energy in the remote area also, like African countries or somewhere where the electricity is not that much easily available. They can run on the solar panel, and they can generate fertilizer when they need it. So they
う
don't
ん
need to do like have a stock or run for the fertilizer. They can also control the nitrogen content. If their soil is not have very less nitrogen, they can treat more to have more nitrogen. If their soil have good nitrogen, then they can treat less to have less content of nitrogen. So the excess nitrogen, which is one of the major problem in the chemical fertilizer, that soil is degraded with excess nitrogen, that can be solved very easily through our machine.
う
Second,
ん
that we mainly we can use in our test the air. So there is no specific condition, any air we can use. So
う
it's
ん
quite cheap. Only the mainly the plasma, yeah, it's still a costly thing, and we're trying to reduce the
This
cost
is, I
by the
see.
company. So it can be
Also,
like more production, more
yes,
cost can reduce.
yes, I understood. Yes, thank you very much for very nice explanation, Pankaj Sensei. So we got two questions in the chat box. Um, First is Pankaj Sensei, thank you so much for wonderful presentations. Yeah. Sorry.
Yeah, I can
Let
read.
me
Okay,
read.
what's
Yeah,
Spark?
yeah,
Yeah,
you
yeah,
can read.
studying about the
Yes.
plasma.
Yeah.
So the
Yes.
Spark
Yes.
is that so if you know that in Sri Lanka, the Sri Lankan government, before the downfall, they suddenly stopped fertilizer. They said that we do organic farming, but the organic farming does not have that much nitrogen content. So it's suddenly loss of the farmers. So to have more people to do organic farming, nitrogen is one of the main species, and that is can be biologically increased or can be chemical increased, but biological is very sensitive with the temperature or pH conditions. So we try to do that. That's our main objective to people can do more organic farming. And in our system, we can use anything. So we can use plant manure, we can use animal manure. So in some countries, the animal manure for organic farming is not allowed. It has some regulation, even in Japan also in some cases, because the animal manure can be the genetically modified. So we can use pure plant manure, and plant manure do not have nitrogen. So we can fix more nitrogen there and use it. And the efficiency and sustainability is quite high, but compared to Haber-Bosch, so we need to see that Haber-Bosch is big reactor. It's produced in tons in one time. So the average cost is little bit less. But in our case, the cost is more than Haber-Bosch, but it is more decentralized. So that calculation need to be added before comparing with the Haber-Bosch, because Haber-Bosch is only ammonia, but this is complete fertilizer that can be used in the plants.
I see. Okay,
Yeah, so,
thank you. Thank you, Pankaj Sensei.
Thank-
So next question is, I have a small question. What are the biggest challenge in scaling up plasma-based nitrogen fixation for agriculture, how does it compare to Haber-Bosch process in terms of efficiency and sustainability?
Yeah, the biggest challenge is that
Mm,
because we are doing without chemical. So the chemical process
without
generally
chemical.
cheap. So
Mm,
we need to use, we are using atmospheric energy. So the energy point of view is the major problem. So we are
mm,
now developing more reactors to decrease the energy efficiency and
mm,
convert near to the Haber-Bosch. But our energy efficiency is field efficiency. Haber-Bosch only generate ammonia. Then it need to fix with urea or nitrate or some other chemical and then transport it. So their energy efficiency directly we cannot compare, but although our is higher, still higher, but we are using it directly on the field. So on the field, this is the decentralized. So the Haber-Bosch cannot be make a small industry. Haber-Bosch is generally very big industry. So if we count the fossil fuel use and other things, we have the most sustainable area. Although the cost is little bit higher right now, I admit that, and we are trying to reduce the cost.
I see. Thank you very much. So, because of the high energy, yeah.
Yeah.
Okay. Okay, thank you very much, Pankaj Sensei. I was wondering, you have many international experience working in India, Belgium, Korea. Which country is more advanced in this research and in the practical utilization of plasma agriculture in your view? And what Japan should do next? Yeah, with the next
So
research.
actually, plasma agriculture is very new, although
New,
new. So
I
it's
see.
not much developed in anywhere.
Okay.
Yeah. In Japan, we have the Center of Nanoplasma, and we have like big projects previously here.
Mm.
So our laboratory is the pioneer in the plasma agriculture in Japan. It is the topmost laboratory in Japan in
Wow.
plasma agriculture.
Wow.
Yeah,
I
and
see.
the plasma in Japan is already good advance in semiconductor processing. Because it used for many years in semiconductors in making chip and other semiconductor devices. But in agriculture point of view, it's beginning. So we are trying to make the Asian hub in our
Wow.
laboratory. So we try to get like some big funding. Yeah, my boss is trying. So to have the central hub we can train the people in Japan or in Asia from our laboratory. And but yeah, we are the pioneer in the
Wow.
world in
Wow.
plasma agriculture.
Wow.
Because in the Google, if you go to plasma agriculture, the first two people are from our laboratory only. So yeah.
Wow. That's really encouraging and very exciting that Japan is reading this research and will be a hub in Asia. Yeah. So, wow, such a privilege to have you here today as a guest speaker talking about the plasma agriculture, very advanced new technology. Thank you so much again,
Thank you. Thank you. Thank you. Thank you very much.
Pankaj Sensei. Yeah, we look forward
ありがとうござ
to
います。
more. Yeah, ありがとうございまし
ありが
た。
とうございます。
何度か
いや
生して。
いや
はい。はい。Thank you very much for all the participants and those who questioned, put it in the chat box. Yeah. You have a wonderful day, rest of the day. And I will return the mic to Harsha Sensei. Thank you, Pankaj 先生。
Thank you. Thank you.
ありがとうございまし
ありがとうございます。
た。
どうもありがとうございます。
はい。
先生、横田先生、ありがとうございました。最後に事務局よりご案内させていただきます。まず、次回のブラウンバッグセミナーのご案内です。次回は来週2月19日水曜日12時10分より九州大学人間環境学研究院教育学部門国際教育交流の 世界的な拡大と外国学歴資格認証の重要性と題し、経営を実施いたします。詳細はホームページをご覧ください。